Good evening, ladies and gentlemen. Welcome to Cal Performances. Tonight's performance is brought to you in part by our season sponsor, Wells Fargo Bank. Please take a moment to turn off your cell phones, and as a reminder, the use of recording devices and cameras of any kind is not permitted in the theater. Thank you, and enjoy the performance.
Good evening. For those of you who don't know me, I'm Robert Bergeneau, Chancellor of UC Berkeley, but for tonight's event, more importantly, Professor of Physics. It's my great pleasure to welcome you to the J. Robert Oppenheimer Lecture in Physics. Berkeley has a long tradition of being a world-leading center of scholarly activity and of bringing to campus the very finest minds to address us in a public forum on great intellectual challenges. It is this Berkeley tradition of great learning and public service that the Department of Physics has arranged for tonight's lecture to be given by world-renowned scholar Stephen Hawking. Professor Hawking has attracted great physics, but he's attracted extraordinary interest from around the world for his work on quantum theories of the cosmos. We here at Berkeley are no exception to the world's fascination with this extraordinary scholar, as witnessed not only by the complete sellout of Zellerbach Hall, but also by the fact that Wheeler Hall, where this event is simulcast, is also completely sold out. Just extraordinary. It is with deepest pleasure that I, on behalf of the entire campus and surrounding community, welcome Professor Stephen Hawking to Berkeley. As many of you will know, this year the College of Letters and Science introduced On the Same Page, a program asking all of our freshmen to read a common book. That book was Stephen Hawking's and Leonard Laudenow's A Briefer History of Time. Faculty and students from many different disciplines took part in discussing this book. In fact, even the chancellor, namely myself, was invited to participate, and last Thursday, I held a small discussion group with a number of our freshmen, embarrassingly, one of whom, at the age of 18, turned out to understand quantum gravity much better than I did. I'd now like to invite Professor Mark Richards, the Executive Dean of the College of Letters and Sciences, and Dean of Physical Sciences, to come forward and tell you more about this wonderful project and how Berkeley is a leader in educating students through unique opportunities such as the Oppenheimer Lecture. Mark.
Thank you very much, Chancellor Bergeneau. I can assure you that Chancellor Bergeneau is here tonight mainly for the physics. I'm here as representative of the College of Letters and Science, and this is a very special occasion on which we're inaugurating a new program, as the Chancellor said, called On the Same Page. And I want to take just a few minutes to describe this program because it's very relevant to the events tonight. Now, the College of Letters and Science is actually most of the University of California at Berkeley. That is, most of the faculty, most of the students, most of the departments you think of, like physics and math and biology and economics, anthropology, history, music, literature. We teach 58 languages here, and we have 38 departments in LNS. It's a very big place, as you might imagine, for an entering freshman can be somewhat of an intimidating experience. And we've been working very hard in the College of Letters and Science to make it feel a bit smaller and a little bit more friendly for their entering freshmen. There are a number of programs that we're very proud of. For example, the Freshman Seminar Series, where we strive to create a seat for every entering freshman to have a close experience with faculty in classes of size 15 to 20 on whimsical subjects sometimes. Also the Discovery courses, which are our flagship breadth courses taught by our very finest instructors for entering freshmen. And also undergraduate research programs to complement this more intimate experience with the faculty, the great faculty of UC Berkeley. And our goal is also for all undergraduates to have this research experience. On the same page is a new program in this direction. The idea has actually been around for some time, bouncing around among the LNS deans. But last May, when Professor Cohen was successful in inviting Stephen Hawking to be the Oppenheimer lecturer, it was just too good an opportunity to pass up. You're all probably familiar with Professor Hawking's famous popular book called A Brief History of Time. Very widely purchased, perhaps not as widely read or understood in its initial formulation. There's a new version of this book, I happen to have a copy here, called A Briefer History of Time, in which Professor Hawking has teamed up with Leonard Mlodinow, who, among other things, is writer of the Star Trek The Next Generation and Feynman's Rainbow, and also happens to be a Berkeley PhD in physics and a resident science writer at Caltech. Also at this time, when we were thinking that this might be a good book and a good way to start the freshman seminar program, one of the closest friends of the College of Letters and Science stepped up to the plate as a donor and offered to buy a copy of this book for every freshman and entering transfer student at UC Berkeley this year. And they all received this. Thank you. So this November, all of our freshmen received a copy of this wonderful book in their mailboxes for light reading over their holidays. Now, On the Same Page has meanings on at least 3 different levels. The obvious meanings being on the same page with the author, being on the same page with your fellow students and your faculty colleagues, but also on the same metaphorical page, because in future years we might well have playwrights or composers or filmmakers instead of just plain old book authors to be the feature of this program. Now, I want you all to think about the last time you read a really great book. And then imagine that all of your friends had just read the same book. And then imagine that you could freely attend discussion sessions with world-renowned experts on every conceivable aspect of that book. And then imagine that you also would have the opportunity to hear the author lecture and to meet the author. This is the experience that we hope to create for all the LNS students, beginning with their freshman year and continuing each year until their graduation. And the message is very clear. Welcome to Berkeley, a place of challenging ideas, a forum for diverse ways of interpreting and experiencing the world around us, and also an arena in which great universal themes are explored and questioned. Certainly this year's author and subject make for a fitting beginning for On the Same Page. It's not too hard to be interested in things like the origin of the universe and the fundamental nature of time. So I want to thank Professor Hawking for helping us make this a very special year in the College of Letters and Science at Cal. I'm also very happy to announce that the LNS deans have already selected next year's book. Are you waiting? It's Lincoln at Gettysburg by author Garry Wills. His brilliant political, historical, and literary analysis of Lincoln's famous speech that recasts the struggle for freedom and human dignity at a critical moment in our nation's history. All of our freshmen, all of our faculty, and hopefully our students and our colleagues and our friends in the community will be on the same page with Lincoln and Garry Wills next September. And this will be also co-sponsored as an event with Cal Performances and Zellerbach Auditorium. So I want to close by thanking you all, everyone here in Zellerbach, everyone out there in Wheeler Auditorium that is also sold out with closed-circuit broadcast, and everyone out there on the webcast for helping us inaugurate On the Same Page this evening. I want to thank Robert Cole, the director of Cal Performances, for being our partner this year and in future years. Marjorie Shapiro, the chair of the physics department, and her colleagues for sharing Stephen Hawking and the Oppenheimer lecturer with us this evening. And also special thanks to staff members Alex Schwartz and Mary Olmstead, who helped to make this event possible this evening. So without further ado, let me introduce Marvin Cohen. Marvin Cohen is a highly distinguished theoretical physicist himself, holder of the very prestigious position of university professor in our physics department here, and he will introduce Professor Hawking. Thank you.
Thank you, Mark. It has been a great pleasure for me to serve on the Oppenheimer Lecture Committee since its inception in 1998. We've been privileged to have outstanding theorists speaking in the series. It started with our first speaker, who was Murray Gell-Mann. Then we had Kip Thorne, Freeman Dyson, Frank Yang, Michael Fisher, our own Bruno Zimino, Robert Laughlin, and tonight our 10th lecturer is Stephen Hawking. In the early lectures, before introducing the speaker, I would say something about Oppenheimer and the history of his involvement with our department. However, in recent years, I've just described the current events related to Oppenheimer. For those of you who are interested in learning more about Oppenheimer and the connection to Berkeley, there is considerable information on the web, and there are a number of books on Oppenheimer. In 2005, we celebrated the World Year of Physics. The idea was to get everybody into physics. And it was the 100th anniversary of the Einstein marvelous year of 1905. And in that year, Einstein did extraordinary work on the sizes of molecules, that was his thesis, on Brownian motion, on relativity, and that's when he wrote down that little E equals mc squared thing. And his, you see it all over Telegraph on t-shirts. And he also did his research on the photoelectric effect, for which he later won the Nobel Prize. The physics community around the world participated in many projects, particularly to try to interest high school students and to reach the public. So it was a year of outreach. And many projects were repeated again last year in 2006, and they've continued to 2007. And there's been a considerable effort worldwide to try to maintain this level of excitement, to see whether or not we can get people to realize that physicists are people too, and that it's a wonderful field to work in. And I view the Oppenheimer Lecture Series as part of this effort. Now, activities related to Oppenheimer intensified during this period and in the past few years, and several new books appeared about his life and about the Manhattan Project. A recording of a speech by Oppenheimer just months after the first atomic bomb test was found by the American Philosophical Society in their archives, and we had the opportunity here in Berkeley to hear this speech. The San Francisco Opera presented the first performance of the opera Dr. Atomic about Oppenheimer and the first atomic bomb test. There were discussions about Oppenheimer on campus, about ethics in science, and about physics. I participated in some of these, and I was very impressed by the large interest of our community. Now, one area of physics in which Oppenheimer made seminal contributions is associated with objects that later were called black holes. Stephen Hawking is also known for his seminal work in this area, and like Oppenheimer, he is widely known by the public at large. And the mention of his name is also a catalyst for initiating intellectual and stimulating discussions. As I indicated, we have tried to make the series of lectures exciting and accessible despite the technical nature of the lectures. There were talks on quarks and quasi-particles, symmetries and supersymmetries, galaxies and strings, and these were given by gifted lecturers using pictures and equations and logical arguments in an attempt to convince us all, you and us, that we can understand much of what nature is about using these tools. Tonight, we are very fortunate to have the opportunity to continue our physics outreach program with an Oppenheimer lecture presented by Professor Stephen Hawking, who is at Cambridge University, where he joined the Department of Applied Mathematics and Theoretical Physics in 1973. Since 1979, he has held the post of Lucasian Professor of Mathematics. This chair was once held by Isaac Newton. Professor Hawking has visited Berkeley before, and he's lectured here in the past. I first met him in 1988 when he spent time here as a Hitchcock lecturer. He gave talks and interacted with many of us, both scientifically and socially. His technical lectures for members of our faculty and students on cosmology and astrophysics were usually focused on subjects he was currently working on, such as black holes. In addition, we were fortunate to have him give general public lectures on slightly broader subjects, like tonight's lecture, which is on a fairly broad subject, the origin of the universe. It's not easy for me as chair of the Oppenheimer Lecture Series to come up with a stimulating speaker who can excite both an academic and public audience. For this reason, I was particularly happy when Stephen agreed to come. This was about 4 years ago when we met at London's Heathrow Airport. I was coming from Edinburgh, and he was going to China. I was complaining about being tired from my short flight from Edinburgh, while he was calmly eating lunch with the look of someone enjoying the anticipation of another adventure. I felt guilty. I was reminded of this again recently when I read an article about Stephen's current plans. When I turned 65, I thought that maybe I should retire and play checkers in the sun and things like this, of this kind. In contrast, Stephen turned 65 this year, and he has decided to take a zero-gravity ride out of Cape Canaveral in a so-called vomit comet. During his flight, he will experience the feeling of being weightless and also the feeling of being very, very heavy. I understand this event is planned for next month. And if that isn't enough, in 2009, Stephen plans a longer and higher flight in a space plane being developed now to reach an altitude of 75 miles. When he's not on a space mission, Stephen Hawking does research, he lectures to broad audiences, and he writes very popular books. He's an inspiration to those who feel they are challenged and limited in some way, and that includes all of us. Right now, I feel more challenged than anyone here because I have to think of next year's Oppenheimer lecture. And this is going to be a very hard act to follow. So please join me in welcoming Stephen Hawking.
only darkness, water, and the great bird Bumper. One day Bumper, in pain from the stomach ache, vomited up the sun. The sun dried up some of the water, leaving land. Still in pain, Bumper vomited up the moon, the stars, and then some animals. The leopard, the crocodile, the turtle, and, finally, man. This creation myth, like many others, tries to answer the questions we all ask. Why are we here? Where did we come from? The answer generally given was that humans were of comparatively recent origin, because it must have been obvious, even at early times, that the human race was improving in knowledge and technology. So it can't have been around that long, or it would have progressed even more. For example, according to Bishop Ussher, the book of Genesis placed the creation of the world at 9 in the morning, on October the 27th, 4004 BC. On the other hand, the physical surroundings, like mountains and rivers, change very little in a human lifetime. They were therefore thought to be a constant background, and either to have existed forever as an empty landscape, or to have been created at the same time as the humans. Not everyone, however, was happy with the idea that the universe had a beginning. For example, Aristotle, the most famous of the Greek philosophers, believed the universe had existed forever. Something eternal is more perfect than something created. He suggested the reason we see progress was that floods, or other natural disasters, had repeatedly set civilization back to the beginning. The motivation for believing in an eternal universe was the desire to avoid invoking divine intervention to create the universe and set it going. Conversely, those who believed the universe had a beginning used it as an argument for the existence of God as the first cause or prime mover of the universe. If one believed that the universe had a beginning, the obvious question was, what happened before the beginning? What was God doing before he made the world? Was he preparing hell for people who asked such questions? The problem of whether or not the universe had a beginning was a great concern to the German philosopher Immanuel Kant. He felt there were logical contradictions, or antinomies, either way. If the universe had a beginning, why did it wait an infinite time before it began? He called that the thesis. On the other hand, if the universe had existed forever, why did it take an infinite time to reach the present stage? He called that the antithesis. Both the thesis and the antithesis depended on Kant's assumption, along with almost everyone else, that time was absolute. That is to say, it went from the infinite past to the infinite future, independently of any universe that might or might not exist in this background. This is still the picture in the mind of many scientists today. However, in 1915, Einstein introduced his revolutionary general theory of relativity. In this, space and time were no longer absolute, no longer a fixed background to events. Instead, they were dynamical quantities that were shaped by the matter and energy in the universe. They were defined only within the universe, so it made no sense to talk of a time before the universe began. It would be like asking for a point south of the South Pole. It is not defined. If the universe was essentially unchanging in time, as was generally assumed before the 1920s, there would be no reason that time should not be defined arbitrarily far back. Any so-called beginning of the universe would be artificial, in the sense that one could extend the history back to earlier times. Thus it might be that the universe was created last year, but with all the memories and physical evidence to look like it was much older. This raises deep philosophical questions about the meaning of existence. I shall deal with these by adopting what is called the positivist approach. In this, the idea is that we interpret the input from our senses in terms of a model we make of the world. One cannot ask whether the model represents reality, only whether it works. A model is a good model if first it interprets a wide range of observations in terms of a simple and elegant model. And second, if the model makes definite predictions that can be tested and possibly falsified by observation. In terms of the positivist approach, one can compare two models of the universe. One in which the universe was created last year, and one in which the universe existed much longer. The model in which the universe existed for longer than a year can explain things like identical twins that have a common cause more than a year ago. On the other hand, the model in which the universe was created last year cannot explain such events. So the first model is better. One cannot ask whether the universe really existed before a year ago, or it just appeared to. In the positivist approach, they are the same. In an unchanging universe, there would be no natural starting point. The situation changed radically, however, when Edwin Hubble began to make observations with the 100-inch telescope on Mount Wilson in the 1920s. Hubble found that stars are not uniformly distributed throughout space, but are gathered together in vast collections called galaxies. By measuring the light from galaxies, Hubble could determine their velocities. He was expecting that as many galaxies would be moving towards us as were moving away. This is what one would have in a universe that was unchanging with time. But to his surprise, Hubble found that nearly all the galaxies were moving away from us. Moreover, the further galaxies were from us, the faster they were moving away. The universe was not unchanging with time, as everyone had thought previously. It was expanding. The distance between distant galaxies was increasing with time. The expansion of the universe was one of the most important intellectual discoveries of the 20th century, or of any century. It transformed the debate about whether the universe had a beginning. If galaxies are moving apart now, they must have been closer together in the past. If their speed had been constant, they would all have been on top of one another about 15 billion years ago. Was this the beginning of the universe? Many scientists were still unhappy with the universe having a beginning, because it seemed to imply that physics broke down. One would have to invoke an outside agency, which for convenience, one can call God, to determine how the universe began. They therefore advanced theories in which the universe was expanding at the present time, but didn't have a beginning. One was the steady-state theory, proposed by Bondi, Gould, and Hoyle in 1948. In the steady-state theory, as galaxies moved apart, the idea was that new galaxies would form from matter that was supposed to be continually being created throughout space. The universe would have existed forever, and would have looked the same at all times. This last property had the great virtue, from a positivist point of view, of being a definite prediction that could be tested by observation. The Cambridge Radio Astronomy Group, under Martin Ryle, did a survey of weak radio sources in the early 1960s. These were distributed fairly uniformly across the sky, indicating that most of the sources lay outside our galaxy. The weaker sources would be further away, on average. The steady-state theory predicted the shape of the graph of the number of sources against source strength. But the observations showed more faint sources than predicted, indicating that the density sources was higher in the past. This was contrary to the basic assumption of the steady-state theory, that everything was constant in time. For this, and other reasons, the steady-state theory was abandoned. Another attempt to avoid the universe having a beginning was the suggestion that there was a previous contracting phase, but because of rotation and local irregularities, the matter would not all fall to the same point. Instead, different parts of the matter would miss each other, and the universe would expand again, with the density remaining finite. Two Russians, Lifshitz and Kaladnikov, actually claimed to have proved that a general contraction without exact symmetry would always lead to a bounce, with the density remaining finite. This result was very convenient for Marxist-Leninist dialectical materialism, because it avoided awkward questions about the creation of the universe. It therefore became an article of faith for Soviet scientists. When Lifshitz and Kaladnikov published their claim, I was a 21-year-old research student, looking for something to complete my PhD thesis. I didn't believe their so-called proof, and set out with Roger Penrose to develop new mathematical techniques to study the question. We showed that the universe couldn't bounce. If Einstein's general theory of relativity is correct, there will be a singularity, a point of infinite density in spacetime curvature, where time has a beginning. Observational evidence to confirm the idea that the universe had a very dense beginning came in October 1965, a few months after my first singularity result, with the discovery of a faint background of microwaves throughout space. These microwaves are the same as those in your microwave oven, but very much less powerful. They would heat your pizza only to minus 271.3 degrees centigrade, not much good for defrosting the pizza, let alone cooking it. You can actually observe these microwaves yourself. Set your television to an empty channel. A few percent of the snow you see on the screen will be caused by this background of microwaves. The only reasonable interpretation of the background is that it is radiation left over from an early very hot and dense state. As the universe expanded, the radiation would have cooled until it is just the faint remnant we observe today. Although the singularity theorems of Penrose and myself predicted that the universe had a beginning, they didn't say how it had begun. The equations of general relativity would break down at the singularity. Thus Einstein's theory cannot predict how the universe will begin, but only how it will evolve once it has begun. There are two attitudes one can take to the results of Penrose and myself. One is that God chose how the universe began, for reasons we could not understand. This was the view of Pope John Paul. At a conference on cosmology in the Vatican, the Pope told the delegates that it was okay to study the universe after it began. But they should not inquire into the beginning itself, because that was the moment of creation, and the work of God. I was glad he didn't realize I had presented a paper at the conference, suggesting how the universe began. I didn't fancy the thought of being handed over to the Inquisition, like Galileo. The other interpretation of our results, which is favored by most scientists, is that it indicates that the general theory of relativity breaks down in the very strong gravitational fields in the early universe. It has to be replaced by a more complete theory. One would expect this anyway, because general relativity does not take account of the small-scale structure of matter, which is governed by quantum theory. This does not matter normally, because the scale of the universe is enormous compared to the microscopic scales of quantum theory. But when the universe is a Planck size, a billion trillion trillionth of a centimeter, the two scales are the same, and quantum theory has to be taken into account. In order to understand the origin of the universe, we need to combine the general theory of relativity with quantum theory. The best way of doing so seems to be to use Feynman's idea of a sum over histories. Richard Feynman was a colorful character who played the bongo drums in a strip joint in Pasadena and was a brilliant physicist at the California Institute of Technology. He proposed that a system got from a state A to a state B by every possible path or history. Each path or history has a certain amplitude or intensity, and the probability of the system going from A to B is given by adding up the amplitudes for each path. There will be a history in which the moon is made of blue cheese, but the amplitude is low, which is bad news for mice. The probability for a state of the universe at the present time is given by adding up the amplitudes for all the histories that end with that state. But how did the history start? This is the origin question in another guise. Does it require a creator to decree how the universe began? Or is the initial state of the universe determined by a law of science? In fact, this question would arise even if the histories of the universe went back to the infinite past. But it is more immediate if the universe began only 15 billion years ago. The problem of what happens at the beginning of time is a bit like the question of what happened at the edge of the world, when people thought the world was flat. Is the world a flat plate, with the sea pouring over the edge? I have tested this experimentally. I have been round the world, and I have not fallen off. As we all know, the problem of what happens at the edge of the world was solved when people realized that the world was not a flat plate, but a curved surface. Time, however, seemed to be different. It appeared to be separate from space, and to be like a model railway track. If it had a beginning, there would have to be someone to set the trains going. Einstein's general theory of relativity unified time and space as spacetime, but time was still different from space, and was like a corridor, which either had a beginning and end, or went on forever. However, when one combines general relativity with quantum theory, Jim Hartle and I realized that time can behave like another direction in space under extreme conditions. This means one can get rid of the problem of time having a beginning, in a similar way in which we got rid of the edge of the world. Suppose the beginning of the universe was like the South Pole of the Earth, with degrees of latitude, playing the role of time. The universe would start as a point at the South Pole. As one moves north, the circles of constant latitude, representing the size of the universe, would expand. To ask what happened before the beginning of the universe would become a meaningless question, because there is nothing south of the South Pole. Time, as measured in degrees of latitude, would have a beginning at the South Pole, but the South Pole is much like any other point, at least so I have been told. I have been to Antarctica, but not to the South Pole. The same laws of nature hold at the South Pole as in other places. This would remove the age-old objection to the universe having a beginning, that it would be a place where the normal laws broke down. The beginning of the universe would be governed by the laws of science. The picture Jim Hartle and I developed of the spontaneous quantum creation of the universe would be a bit like the formation of bubbles of steam in boiling water. The idea is that the most probable histories of the universe would be like the surfaces of the bubbles. Many small bubbles would appear and then disappear again. These would correspond to many universes that would expand, but would collapse again while still of microscopic size. They are possible alternative universes, but they are not of much interest, since they do not last long enough to develop galaxies and stars, let alone intelligent life. A few of the little bubbles, however, would grow to a certain size at which they are safe from recollapse. They will continue to expand at an ever-increasing rate, and will form the bubbles we see. They will correspond to universes that would start off expanding at an ever-increasing rate. This is called inflation, like the way prices go up every year. The world record for inflation was in Germany after the First World War. Prices rose by a factor of 10 million in a period of 18 months. But that was nothing compared to inflation in the early universe. The universe expanded by a factor of million trillion in a tiny fraction of a second. Unlike inflation in prices, inflation in the early universe was a very good thing. It produced a very large and uniform universe, just as we observe. However, it would not be completely uniform. In the sum over histories that are very slightly irregular, will have almost as high probabilities as a completely uniform and regular history. The theory therefore predicts that the early universe is likely to be slightly non-uniform. These irregularities would produce small variations in the intensity of the microwave background from different directions. The microwave background has been observed by the MAP satellite, and was found to have exactly the kind of variations predicted. So we know we are on the right lines. The irregularities in the early universe will mean that some regions will have slightly higher density than others. The gravitational attraction of the extra density will slow the expansion of the region, and can eventually cause the region to collapse to form galaxies and stars. So look well at the map of the microwave sky. It is a blueprint for all the structure in the universe. We are the product of quantum fluctuations in the very early universe. God really does play dice. We have made tremendous progress in cosmology in the last 100 years. The general theory of relativity and the discovery of the expansion of the universe shattered the old picture of an ever-existing, an everlasting universe. Instead, general relativity predicted that the universe, and time itself, would begin in the Big Bang. It also predicted that time would come to an end in black holes. The discovery of the cosmic microwave background and observations of black holes support these conclusions. This is a profound change in our picture of the universe and of reality itself. Although the general theory of relativity predicted that the universe must have come from a period of high curvature in the past, it could not predict how the universe would emerge from the Big Bang. Thus, general relativity on its own cannot answer the central question in cosmology: why is the universe the way it is? However, if general relativity is combined with quantum theory, it may be possible to predict how the universe would start. It would initially expand at an ever-increasing rate. During this so-called inflationary period, the marriage of the two theories predicted that small fluctuations would develop and lead to the formation of galaxies, stars, and all the other structure in the universe. This is confirmed by observations of small non-uniformities in the cosmic microwave background with exactly the predicted properties. So it seems we are on our way to understanding the origin of the universe, though much more work will be needed. A new window on the very early universe will be opened when we can detect gravitational waves by accurately measuring the distances between spacecraft. Gravitational waves propagate freely to us from earliest times, unimpeded by any intervening material. By contrast, light is scattered many times by free electrons. The scattering goes on until the electrons freeze out, when the universe is 300,000 years old. Despite having had some great successes, not everything is solved. We do not yet have a good theoretical understanding of the observations that the expansion of the universe is accelerating again after a long period of slowing down. Without such an understanding, we cannot be sure of the future of the universe. Will it continue to expand forever? Is inflation a law of nature? Or will the universe eventually collapse again? New observational results and theoretical advances are coming in rapidly. Cosmology is a very exciting and active subject. We are getting close to answering the age-old questions. Why are we here? Where did we come from? Thank you for listening to me.
Professor Hawking has agreed to answer some questions, and so we gathered a few of the most popular questions, and there were 5. And my job is to read all 5 questions, and he will answer all 5 questions with one extended answer. Some of these questions bear on things he's already said, but you have to realize the questions were made in advance of his talk. Question 1, do we know for certain how the universe began? Question 2, the problem for most people in trying to grasp all this is if the Big Bang began at all, what was before the Big Bang? I'm afraid I'm going to end up in hell. Question 3 is, how will the universe end and when? Question 4, you say your goal is simple, a complete understanding of the universe. And the question goes on to say, why is it as it is, and why does it exist at all? How close are we, and can science ever answer, and this is in big letters, why it exists in the first place? And question 5 is a very good one. What are the pressing big questions that are left? Professor Hawking.
We are fairly sure the universe began with a period of accelerating expansion. This is called inflation because the size of the universe grows in the way prices go up in some countries. The inflation in the early universe is much more rapid than our financial inflation. The universe expanded by a factor of 1,000,000 trillion in a tiny fraction of a second. Inflation in the size of the universe is a good thing, unlike inflation in prices. It would produce a very large and very smooth universe, with just the right amount of irregularity to account for the formation of galaxies, stars, and ultimately, human beings. How did this inflation start? How can one describe the universe at the beginning of time? I now think I can show how the universe was spontaneously created out of nothing, according to the laws of science. The universe exists because general relativity and quantum theory allow and require it to exist. If I'm right, the universe is self-contained and governed by science alone. In time, we can hope to understand it completely. We have long enough, as the universe should last forever. Eternity is a very long time, especially towards the end, as Woody Allen said. Thank you.